This PhysCast will look at the quantum mechanical description of the hydrogen atom. Beginning with an interpretation step, this question is involving quantized energy states of an atom. These energy states are described in terms of quantum numbers, and we want to understand what states are possible in terms of the quantum numbers describing them. In addition, we also want to be able to calculate the energies of these states. In our developed stage, we'd typically like to draw a diagram of some kind. So we know it's a hydrogen atom, which is a proton at the nucleus and some kind of arrangement of an electron moving around that. But in fact, we know from a quantum mechanical point of view, this picture is completely wrong. That's not how we model an atom using quantum mechanical descriptions. In fact, it's quite challenging to do a simple sketch of the quantum mechanical model, given that the electron's location is described in terms of probabilities rather than an orbit. So instead, we know that we're going to describe our atom in terms of quantum numbers, beginning with the principal quantum number we call n, and the possible values that can take are all integer values, non-zero integer values, so it could be 1 or 2 or 3, etc. And we know, in fact, in this problem, we're told the principal quantum number is n equals 2. The states are also described by another quantum number, namely the orbital quantum number, quantizing the angular momentum of the particular state, and that's small l, and the values that small l can take actually depend upon the value of the principal quantum number, and it ranges from 0 in integer steps up to 1 less than our principal quantum number. So depending upon what the principal quantum number of the state happens to be, that tells us what possible values the orbital quantum number can have. In addition to that, there's the magnetic orbital quantum number, which actually tells us something about the direction of the angular momentum, and it's an m with a subscript l, and once again its values depend upon another quantum number, namely the orbital quantum number, and it will range possible values from minus l in integer steps up to plus l. So depending upon what value for the orbital quantum number, that will tell us what possible values the magnetic orbital quantum number could have. Regarding the calculation of energy, we know that the energy in the quantum model of the atom for a hydrogen atom depends upon the principal quantum number n, and it is in fact negative 1 over that principal quantum number squared, multiplied by a combination of fundamental constants, h bar squared, that's Planck's constant divided by 2 pi, all squared, divided by 2 times the electron mass, multiplied by the square of the Bohr radius. It's a reasonably complicated expression, but everything in that second factor there is a fundamental constant, so we can actually rewrite this as minus 13.6 divided by n squared in units of electron volts, which is a convenient unit to use when we're dealing with things on the atomic scale. So now we can move to our evaluation part of the solution, where now the possible states depending upon these 3 quantum numbers, and in fact there is another thing we might consider if we were concerned with the electron spin. That's another quantized angular momentum in the problem, but our questions told us for the time being to ignore the electron spin. So really we just need to know what are the possible combinations of quantum numbers for n equals 2, the principal quantum number equals 2. So for n equal to 2, we know that our orbital quantum number L can go from 0 up to n minus 1. So in this case it can go from 0 up to 2 minus 1, which is 1. So in fact we only have 2 possible values in this problem for the orbital quantum number. So we could have L equals 0, or we could have L equals 1. And then depending upon the value for that L quantum number, we have the magnetic quantum number ranging from minus L to plus L in integer steps. So for that first possible value of L, 0, from minus 0 to plus 0 in integer steps, well, that's just only one possibility. That equals 0. For the L equals 1 states, we can go from minus 1 to plus 1 in integer steps. Well, that gives us minus 1 0, and plus 1. So if we were to now list the possible states, we might list them in terms of those three quantum numbers, n, l, and n subscript l. The possible combinations we have here would be, well, they're all going to have n equals 2, that's what the question tells us, and we might have l equals 0, ml equals 0. We could have n equals 2, l equals 1, and ml equals minus 1. We could have n equals 2, l equals 1, ml equals 0, and we could have n equals 2, l equals 1, ml equals plus 1. So there are in fact 4 possible states for the n equals 2 principal quantum number for hydrogen, depending upon those allowed possibilities for the L quantum number, orbital quantum number, and the ML, the magnetic orbital quantum number. Let's move our solution up a little, because the last thing we want to be able to do here is to calculate the energies of these states. And as you can see, the energies of these states only depends upon the principal quantum number n, and all of these states, as indicated in the question, all have n equals 2. So this will simply be, for all of these 4 states, 13.6 divided by 2 squared. This is in units of electron volts, and we do that, we find it's minus 3.4 electron volts for each state. And again, we've ignored the electron spin. If you go back and look at your notes on atomic structure, you'll see that if you include electron spin, the coupling of that spin to the orbital angular momentum can actually cause a very small splitting, a small difference in the energy levels of some of these states. Finally here, for our assess step, we might just consider for the time being that what if we did include electron spin? If we did that, then we would have twice as many states. The reason for that is the electron spin has 2 possible quantum numbers. It can be plus a half or minus a half. So each of these 4 states basically could have the same values for those 3 quantum numbers, and a plus half spin quantum number or a minus half spin quantum number. So our 4 states will become 8 states, and that makes sense if you go back and look and see that if we consider a multi-electron atom, then the n equals 2 shell with 8 electrons. So indeed these 4 states that we've found by ignoring electron spin actually become 8 states if we include electron spin, and that's consistent with that n equals 2 shell being filled with 8 electrons.